Okay, first thing we're going to do is look at glycolysis. So, like we said, it's a process that takes place in the cytoplasm of all tissues. Remember, you have to know where every process happens, both on the cellular level and on the tissue level. So, cytoplasm of everywhere, all of you. So, energy making process that starts processing your carbohydrates with the end goal of making energy in mind. So you have to know that. You also have to know what molecule makes what molecule. So glucose makes glucose 6 phosphate, makes fructose 6 phosphate, so on, down to pyruvate. When we did this in the first place, we talked about the reactions, what's going on, such as when we're going from glucose to pyruvate, we're using an ATP. So we're taking the phosphate off of an ATP, leaving us an ADP, putting the phosphate onto carbon 6 of the glucose. So that's why it becomes glucose 6 phosphate. And that was our reaction. So we use the energy, of course, though, from the high energy phosphate bond. So get really keyed into when I'm making or using ATP, and we've talked about this. For me to make ATP out of ADP, I have to have enough energy to replace the energy of the high energy phosphate bond. That's like paying in energy to do something. Or if I see an ATP getting used, being converted to ADP, that means that I broke a high energy phosphate bond. When I do that, that means I need the energy. I might use the phosphate for something or I might not. So I need the energy. So kind of watch what's going on with ATP. It's like when you're shopping, looking at price tags. The ATP being used or made is telling you either I need energy to drive this reaction, so I broke a high energy phosphate bond, or I had energy to do something. If I put a phosphate onto ADP and got ATP, the something, of course, I did was harness that energy into the high energy phosphate bond. So keep an eye on that. So anyway, of course, I have to know what makes what. Really nice multiple choice questions, because keep in mind, especially on a timed test, your multiple choice questions have to be kind of short and sweet, even though you might not see the sweet in them. But to stay within the timing we need to stay within, they need to be short. So what makes really good multiple choice questions. Keep in mind, though, reading and paying attention to what the question is asking is half your battle. And I know how crazy this sounds, but when I go back and look at the stats from questions, this is something I see. Let's say it's a question about glucose 6 phosphate. Be careful. Is the question asking you what forms glucose 6 phosphate, in which case the answer would be glucose? Or is the question asking you what does glucose 6 phosphate form? In which case the answer would be fructose 6 phosphate. Both of these will get offered as the answer and the distractor. So you can read fast, see one thing, think you're seeing something else, see the answer right in front of you, and think, good to go. The answer I think it is here. I must be right. No, somebody's just kind of getting ahead of you with what errors you could make. So anyway, what makes what is fair game. So be prepared for that. And again, like we've talked about so many times, if if you know if you look at what might I get asked here, let me predict the possible questions I could get on this topic. If you can do that, odds are you're going to be correct. That's going to direct your studying. There's nothing worse than trying to study and you're looking at something like, where do I start? If you can predict the questions, there's your where do I start answer. So what makes what? Absolutely. Then every process has regulatory steps which of course are regulated by regulatory enzymes. Gotta know those. And I'm abbreviating because we've done them so many times in the notes. You have to know those, and you have to know what regulates them. Hexokinase is regulated by glucose 6-phosphate. I'm going to abbreviate in this as much as I chased you guys not to abbreviate, but I'll say it as I abbreviate it. It's just time and space. In your notes, again, if the word starts with G, don't abbreviate it. Write it out. If you don't, you will regret it, because there's so many words that start with G. Of course, the second letter is L, the third letter is Y or U. This is the point after we get through these topics where they all feel like they're blending together on you. So the other term we hear here is product inhibition. Phosphofructokinase is regulated by citrate and by energy. Again, remember how we can say we have energy or we don't have energy. If I have ATP, I have energy. If I have NADH, we're going to assume we have energy because I have what I need to make energy. I have ATP equivalents. I have electron carriers loaded up with electrons. I have reducing equivalents. I'm not very good at remembering to say that word, but a reducing equivalent is an ATP equivalent. It's been reduced. It's an energy-containing molecule that's ready to go and give you the energy, of course, in the form of ATP. So if I don't have energy, we say that sometimes in a very black and white statement. The truth is, you have ATP and ADP all at the same time, all the time. However, if a multiple choice question says to you, you have ADP, take that as a very black and white statement that means you don't have enough ATP. Or if I have NAD, take that as the same black and white statement. I don't have NADH, so I don't, in effect, have the ingredients for ATP, so I don't have ATP. So all the different ways you can say you do or don't have energy. Also with this one, citrate is not a molecule in glycolysis. That doesn't matter. Don't worry about it. Citrate is in the Krebs cycle along the route to making you ATP, so that's fine. It can still regulate back here at phosphofructokinase, so don't get thrown off by that. Pyruvate kinase then is regulated by two things. Fructose 1,6-bisphosphate, safe to abbreviate fructose with an F, phosphate with a P. We don't have any other F words or P words. So fructose 1,6-bisphosphate back here regulates my pyruvate kinase and energy. So fructose 1,6-bisphosphate is the only activator in this list, but don't memorize that. Reason your way through it, like we've said so many times. If I already have lots of product, glucose 6-phosphate, do I need to make more? No. So shut down hexokinase. If I already have citrate or energy, citrate being a molecule well along the way to making energy, or all the way, or already have energy, do I need to run this energy making process that is glycolysis? No. I could save the glucose for later. So they both inhibit. Energy again inhibits. Why do I need to run this energy making process if I already have energy? I don't. I could save the glycolysis for later. However, the fructose 1,6-bisphosphate is an activator. So the only activator. The way we talked about that, and let me remind you, was this. Let's say you've got a ton of work ahead of you. You guys have a rough week this week with a bunch of quizzes and tests and midterms and whatever. So you have all this stuff to do, and I add more work. Well, what are you going to do? What you're going to do, at least in theory, I've heard other suggestions of what you might do if I did that to you. But in theory, what you're going to do when you have a bunch of work and you know you have more work coming is clear out the work you have. So you know you have all this fructose 1,6-bisphosphate. Pyruvate kinase is going to say, let me get rid of this phosphoryl pyruvate that I have now because I know more is coming my way. Let me get all these projects done that I have now because I know I'm going to have another project assigned to me. So this is my only activator on the list. But again, like I said, don't memorize it, reason your way through it. So regulatory enzymes and what regulates them. Really, really good stuff to know because, of course, everybody loves giving you pairing questions. Here's the regulatory enzyme and here's the regulator. Here's, 4 sets of those. Which one of those is incorrect? Which one did I put an incorrect regulator with the regulatory enzyme for? So watch out for those. Then, here and there, you've got to know other enzymes that have a particular significance in life. In the case of glycolysis, that's phosphoglycerate kinase. So phosphoglycerate kinase, its significance in life is that it's the enzyme that catalyzes the first reaction of glycolysis in which you form ATP. So which of the following enzymes catalyzes the first reaction of glycolysis in which you form ATP? Your answer will be phosphoglycerate kinase. So another good thing to know. Then the other thing with glycolysis that you need to know is how many ATP. So let's go back and talk about how many ATP questions for a second. So to answer a how many ATP question, there's certain things you need to know, certain pieces of information you need. So the first one is per what? What's my reference point? So that's the one when we were talking about it in class, we said, let's pretend I'm your accountant and we're talking about your office. And I said to you, how much money did you make in your office? Well, you're going to say to me, well, per what? Per last year, per last month, per last week, whatever. So per what? In terms, in terms of glycolysis, it's going to be per before or after the split. So per before or after the split, because of course it's a factor of 2 difference. So be careful of that, especially when we're in the Krebs cycle and places further and further away from the split, because the further away from that split you get, the higher the probability of you forgetting that you did that split. Next thing you have to know is net or yield versus made. So as much as you guys hate my money analogies, we're going to do it again. Do you mean profit or do you mean gross? So back to your office. Let's say we're talking about your office. Last month, I'm still your accountant. How much money came into your office last month? Well, do you mean how much money came in, like before I paid any bills, as in gross? That's how many made, or how much money did I make? Or do you mean how much money was left after I paid the bills? Profit. That's my net or my yield. The net or yield versus made tends to be a glycolysis concept. So what did I do? What I did was, per glucose, I made for ATP, 1, 2, 3, 4, cost me 2. So my net or my yield is 2 ATP per glucose. So made 4, cost me 2, my net or my yield is 2. Then, third thing you gotta know is, are we talking about real ATP? We'll say real ones in quotes because nobody will ever say that to you, or equivalents. This tends to be a Krebs concept, Krebs cycle concept. So again, you in your office, the end of the day, you walk up to the front desk and your front desk staff has your credit card slips for the day, you print it out, has some checks, some people still write checks, has some cash, has insurance forms, whatever. And you say, oh, what did we take in today? they're going to say to you, do you mean actual cash we took in? Or do you mean once we get all this turned into money, your insurance slips, your credit card stuff, your whatever, do you mean that much? So you're going to have to clarify to get that answer. So the question is either going to say ATP equivalence, that's your NADH, your FADH2, stuff like that. And of course, ATP is an ATP equivalent. If we're counting it all up, that means everything. Or no one's ever going to say real ones. They're just going to say how many ATP. But if they don't say equivalence, they don't mean equivalence. Trust yourself. That's where you guys start second guessing yourselves. They don't say equivalence, they mean real ones. How many ATP? How many of the real thing did you make? Okay, so you have to know those things to be able to answer your how many ATP questions. And of course, like we said, per what is going to refer to glycolysis. Whether you're talking about glycolysis or not, the split is going to be the factor of two difference. And the net or yield versus made is typically a glycolysis concept. Okay, so that's our glycolysis review. Now, let's talk about the Cori cycle. Oops. So, we took glucose to pyruvate in glycolysis. We did not need oxygen to do that. However, once we get there, oxygen or pyruvate, looks around and says, do I have oxygen? If I have sufficient oxygen, now I'm going to go to the pyruvate dehydrogenase complex, Krebs, electron transport, all my stuff, and get my ATP. If I don't have sufficient oxygen, that now is going to be my Cori cycle. So my Cori cycle is this do-over loop that takes the pyruvate when you don't have enough oxygen and does a do-over loop, gets the glucose back so you can send it out into the bloodstream and try this again, hoping that you have enough oxygen this time. Remember, I'm not going to ask it this way because I think it's really stupid, but sometimes we'll call sufficient oxygen aerobic glycolysis, even though glycolysis is anaerobic, and it's probably not even a glycolysis question when we're doing that. We'll call insufficient anaerobic glycolysis. And again, it's a Cori cycle question, not even a glycolysis question. And I won't ask you that way. I hate it. So I won't do it. But in case somebody else asks you an aerobic or an anaerobic glycolysis question, I don't want you thinking, well, hang on here. I only learned regular glycolysis. I didn't learn that. Well, regular glycolysis is glycolysis, or glycolysis is regular glycolysis. Your ticket from glucose to pyruvate won't change. It's just a matter of what you have going on in the oxygen department when you get there. So let's talk about the Cori cycle. So in the Cori cycle, we'll use some Palmer purple. Most often, you're going to hear the Cori cycle story told in the context of an exercising skeletal muscle. So I have a skeletal muscle that's exercising, and I want to keep it going, keep it exercising. So to do that, I need ATP to do that. So how do I get ATP? Well, I start out with my glucose, take my glucose to pyruvate. I want to take it into the pyruvate dehydrogenase complex, into the Krebs cycle, into electron transport, and do all my stuff to make ATP. However, I have insufficient oxygen, so I can't do that. So instead, I'm going to go now to lactate. The enzyme that's going to take me there is lactate dehydrogenase. So I'm going to get lactate instead in the muscle. Great. It's not getting me energy. That's kind of not helping me. So what I need to do then with that lactate is I need to send it to the liver. So liver's like everybody's mama. And I know you're tired of hearing me say that, but that's okay. Sometimes when you're tired of hearing me say something, make sure you remember it. So what do I mean by the liver is like everybody's mama? The liver takes care of everybody. So the liver takes care of everybody through the bloodstream. Stuff circulates in the blood to where? To all your tissues, everybody. Also, the liver's your cleanup crew. I have a molecule I don't need, don't want. How do I get rid of it? I send it to the liver. So these are kind of Hail Mary answers. You're sitting in front of a question and you're thinking, I have no idea where this molecule goes. Where do I go? What do I do? Well, if it's a molecule you don't want and you don't remember where it goes, odds are it's going to the liver for the liver to get rid of it. So I'm going to send my lactate then back to the liver. Well, I didn't really want lactate. I just kind of got it anyway. So I'm going to convert it back to pyruvate. The enzyme that does that is lactate dehydrogenase. Hang on here. How do I know which way my lactate dehydrogenase is going to go? Well, think about what regulates a reversible reaction. Remember, delta G equals 0. So what regulates a reversible reaction? Equilibrium, right? So my reaction's sitting there in equilibrium. Then I add or take away product or reactant. I mess up the equilibrium. What did Le Chatelier say happens? Well, I adjust and go to a new equilibrium. I reestablish equilibrium. So I was sitting here in equilibrium, and all of a sudden I made a bunch of pyruvate. That's going to make me make a bunch of lactate, send me in that direction. Or I'm sitting here in equilibrium. All of a sudden I dump a bunch of lactate in, makes me make lactate. That's going to make me make more pyruvate. So add or take away, product or reactant, I'm going to end up with more or less, whichever it is, of both. So I get my pyruvate back then. Well, great. I don't really want that. I want glucose. So I'm going to do gluconeogenesis, which we hadn't done yet when we first did the Cori cycle, but you've done it now. I'm going to do gluconeogenesis, get glucose back, send that back into the bloodstream. It can go back to that exercising skeletal muscle, and maybe by then I'll have slowed down and I'll have enough oxygen. If not, I'll do this again and again and again. So what are the common things to get asked about the Cori cycle? Well, really common one is the enzyme, lactate dehydrogenase. Of course, keep in mind what a beautiful distractor is for lactate dehydrogenase. How about pyruvate dehydrogenase? Pretty mean one, right? But very possible one, so be careful there. Also, what's another good thing to ask? Well, how about which way am I going with the pyruvate and the lactate? Which one am I making where? I'm making lactate in the muscle. I'm making pyruvate in the liver. So, do you know which direction you're going? So those are really common things to get asked about the Cori cycle. We'll do a separate video now so I can change the screen share to do the Krebs cycle.